All right. So let's get into this a little bit. Um, the point of what we're doing today is we need to sit down and kind of have a conversation about how in the world do we start proving things. Okay, because at this point we have the logic down. We have conjecture, counterexample, all of the things with conditionals, biconditionals, converse, inverse, contrapositive. That was all of last week. So we understand logic to a necessary point for what we need this week, okay? This week, we need to start by having a conversation about how do you do a proof, okay? What is it that you do to do a proof? Cool? That's what we're going to do today. So, anytime you prove something, okay, I want you to think of it like it's a court case. I don't know if any of you guys watch any like court cases, CSI, like investigation stuff, but like if you're going to prove something, you need to understand what happened. So like let's say somebody rammed their car into a building or something, right? That is what happened. That's the given information that you need to work off of to prove, well, is the person guilty or not, right? So when we're proving something, the very first thing that I want to talk about is the given information. What's happened? What's going on here, okay? So on the top left box, you see right there where it says the word given, right? This is called our bank of reasoning. This is like all of the different possible reasons I could give for stuff, for like my testimony, right? So if I look at the word given, what I'm talking about there is, what do I know? Okay, what do I know? I don't ever have to prove that that happened. It just did. Okay, so when I prove anything, the very first statement I'm going to say every single time, and if that's something you want to remember, I'd probably write that down. I'm going to say always first. Okay, it's always the very first thing I talk about is the given information, and the problem will tell it to me. It will say, "This is what's given." Okay, go from there. Ladies, I'll make sure we can get through this right now. I appreciate it. So, the definition of congruence is my next piece here, okay? The definition of congruence goes something like this. If I know that two things are congruent, well then their measurements are equal. Think about it. If they're congruent, that means that the lengths, if I were to actually measure them, then they're equal. So if I see in a circumstance something along the lines of, well, this tells me it's congruent, okay, and then it says that those are equal, that tells me I can say that because of the definition of congruence. That's how it works, okay? And we'll see that a little bit in example one. So we'll see that happen. So before I move forward, what questions do you have about what I mean by given information or the definition of congruence? Okay. Now the segment addition postulate should look pretty familiar. In fact, it's what you were just doing today, right? If I have some sort of line segment A to C, right? Some sort of line segment A to C, well then if B is somewhere inside of that, it's if I take AB plus BC, I get all the way across to AC. We've seen that before, right? It looks something kind of like, I'm going to draw the picture here, but it should look something kind of like this, right? Here's A, somewhere in the middle is B, and then C is at the very end. I can take A to B plus B to C and get all the way across from A to C. And we call that the segment addition postulate. Postulate's a fancy word. It just means a reason that we don't prove but makes sense. Okay? Some other things we know are totally possible. We learned this in middle school. If I know what X is, I can plug it in. We call that substitution, right? You substitute in something for something else, right? It's like you go to the lunch line and you're like, I don't want square pizza, I want applesauce. So you say, I'm going to swap that out. Cool? So substitution, all I'm saying here is if A equals B, right? So if I have something that's the same as something else, I can swap them back and forth. I can substitute them for each other. Okay? Before I move forward, I want to make sure we can digest this together. What questions do you have? two last ones, and then I want to do some demonstrations with some things. So, definition of a midpoint. We used that a little bit on that first problem of the whole midpoint thing, right? The definition of a midpoint is it's the point in the middle that makes two equal segments, right? So, for example, let's say I had A to C and B was in the exact middle. We used those little dashes to say that those measurements matched up, right? The midpoint definition says those two segments have the same measurement. They're equal, right? And then the last one, you know what you can do with math? You can simplify. So if I have a fraction or I have some sort of equation, I can combine like terms. I can simplify things down to make it much easier for me to work with. So these are all just reasons I can give for why things happen. So when I was asking you, step by step by step, what's happening? This is kind of what I'm saying is, why was I able to say that I could add them together? Well, the segment addition postulate said I can. Or why did I know that I could substitute in the variable? Because I'm allowed to substitute, right? These are our bank of reasons. They are the reasons why we are able to do things. And a lot of the times we take it for granted, but it's the same thing as if I were trying to fix my car, right? Let's say you're driving down the highway and your car breaks down on the side of the road and you're like, well, crap, I don't have any coolant that I need to put in because my engine's overheating. How in the world do I deal with that situation? Do I just call a tow? That's expensive. I don't know if I quite have the insurance for that. Well, what if I knew a little bit of how to operate under the hood, right? In the same way, math just operates, and a lot of the time we just say, well, yeah, of course it works that way because we're told it does. But true mastery looks like, well, how do I know it works? How do I make sure that the engine's running correctly so my car drives the right way, right? So this is what we're doing is we're looking under the hood and we're making sure that each of these steps looks correct, because if any domino is out of place, we're doing bad math and it doesn't work out the way it should. So what questions do you guys have about any of these reasons we've talked about so far? Okay, I need some help. I just need two people really quickly who wouldn't mind helping me for just a moment here up at the front. Okay, cool. I'll just have you guys. Thank you. I appreciate it. So, you guys see how there's X's here? Go ahead and stand on one. Each of you go ahead and stand on one of the X's. So, here's what I want you guys to do. Turn towards each other. There we go. So, I'm going to imagine with me here, between them is a mirror. Okay? Imagine there's a mirror. So, a mirror is reflective. I want Wyatt, go ahead and take your right hand and move it around. So if there's a mirror, what does the mirror look like? Does this look correct? What does it? His right hand is moving. If he's looking in a mirror, what should Josh's hand be doing? Would it be the other one? Yeah, right. Your left hand's the one that's moving, right? Does that make sense? If there's like a mirror right here, if his right hand is moving, then it's like the opposite for him, right? Thank you, I appreciate that. So, here's what I want to get at. First and foremost is something about mirrors. They're reflective. I mean, if you're looking in the mirror, it's pretty reflective. So, in a moment, we'll talk about the reflexive property in that same sort of way. But then, if you're looking in a mirror, there's something called symmetry as well. That idea that if Wyatt was moving his right hand, Josh had to move his left. It was symmetric. It had to match. Now, here's the last one. My goal of this new game that I just created in my head is this. See, I have a pen, like a marker right here. I want to try to be able to get this over to Wyatt. So in order to do that, I have a couple ways. Boom, right? I can just toss it over to Wyatt, and Wyatt has the marker now. Thank you, I appreciate it. So I could just go straight to him. Or you know what I could also do? I could give it over here to Josh. Josh has the marker, and then Josh could probably hand that over to Wyatt as well. All right, you see that? I was able to get it to the same destination multiple ways, either just straight over to him or through someone in the middle, okay? And we'll talk about that in a moment. Thank you, guys. You're welcome to find your seats. So, here's what I'm getting at with all of this. Hopefully that visual demonstration shows us something useful. The reflexive property. Mirrors are reflective. They reflect things. And so the reflexive property says this. A equals A. If I look in the mirror, I see myself, right? At least I should. If I don't, then that's a little creepy, right? But a number is always equal to itself. I'm never going to have a situation where 1 equals 0. That doesn't make sense. They're not the same thing, okay? So the reflexive property is like a mirror. You look in the mirror, and if you see yourself, you're good to go. Whereas the symmetric property was this thing that Wyatt and Josh did with their right hand and their left hand, right? It says something like this. If A equals B, well then B equals A, which seems redundant, but what's happening here is exactly what we saw with Wyatt and Josh's hands, was that if I move my right hand, it had to match with the left. I can swap the order and it stays the same, okay? So if I swap the order around a little bit, well then I call that the symmetric property. It's like butterfly wings, right? Butterflies have the same pattern on both wings, it's just backwards from each other. So they can swap, it's the same pattern, just opposite, okay? And now this weird thing with the transitive property, that marker thing that I did, right? Here's what I want you to think of. Transitive kind of sounds like transport, like I'm transporting something. So if I wanted to transport the marker over to Wyatt, I had to probably go through Josh, right? So it says if A equals B, right? If A equals B, and B equals C, what could I conclude? If A equals B and B equals C, then what can I conclude here? A equals C. Yeah, no, totally. Because imagine I am A, Josh is B, Wyatt is C. Think about it. If I go to Josh, and then Josh goes to Wyatt, then I go to Wyatt. It gets to the same place at the end, right? So what that tells me is if I have a bunch of things that are all equal to each other, I can change that around and substitute how I wish because they're all just equal to each other. And that's what's happening here is I wanted to get it to Wyatt, so I had to go through Josh to get there. I'm equal to Josh, Josh is equal to Wyatt, so I'm equal to Wyatt. We're all equal to each other. Cool? So what questions do you guys have about the reflexive, symmetric, or transitive properties here? Last part, and then we'll do example 1. So, addition property, subtraction property, division property, multiplication property. You know what's really cool about math is you can just add the same thing on both sides, or subtract the same thing on both sides, or multiply the same thing on both sides, or divide the same thing on both sides. And it works. These are our reasons why, right? The addition property. I could say A plus C equals B plus C. You see how we added C on both sides? It's like the same number we're adding. If 1 equals 1 and we add 1 on both sides, 2 equals 2. That makes sense. And if we can add, we can also subtract. A minus C equals B minus C. We're allowed to subtract on both sides. We can divide on both sides. A divided by C equals B divided by C. And lastly, A times C equals B times C. Right? All of these are just properties that we know work because we've tried and tested them for a long time and they work. If you ever do want to look into this, I think this is just the weirdest thing. The actual proof of 1 plus 1 equals 2 is 278 pages long. So if you do ever want to look into that, proving it uses all of these reasons and properties we just kind of took in some notes. But yeah, the actual proof, having to sequence them correctly, took 278 pages. But we do know that 1 plus 1 actually does equal 2. We do that for every number? Well, if we know 1 plus 1, we can get the rest. So, yeah. Any questions about these properties? How we might apply them, how they work? Okay, let's see the value of what in the world we use these for. So here's what we've got. It says we need to write the correct statement and reason to create a two-column proof. You know when I told you guys we were going to have like the math on one side and then like you were giving me the reasons on the other? That is called a two-column proof because you have two columns. So let's look at it. The given information says this. This is our like case file that we're about to prove in court, okay? It says C to E, if we're looking, C to E is right about here, is congruent, you see that symbol congruent, with F to E. So I'm going to put some dashes right there. You see that? I'm going to put some dashes. They're congruent to each other. And then it also says E to D is congruent with E to G. So I'm going to put two dashes in each of these to show that those ones match. All right? So C to E and F to E match. E to D and E to G match. We need to use that information to prove definitively that all the way from C to D is the same length as all the way from F to G. So another way to rewrite this in case it's not clear what's happening, I'm going to put F, E, and then G is all the way over here. So we have F, E, G. And then down here we have C, there's E again, and then D. All right? Something kind of like this. And we know that these two match, and we know that these two match. And so using that information, we need to show the entire length across for both of them are the same length. Which makes sense. If we look at it, we're like, well, of course it does, right? But how do we know? Are we absolutely sure? So, first reason why, well, it says the same information as what we started with. Why is that? What reason could we give for that? You can look at your bank of reasons on the left if you need to look. What reason could we give for that? Yeah, what are you thinking? Maybe. What was the very first thing we started with at the top? Given. And what did I say to write down if it was something you wanted to remember? It's always first. Anytime you ever do a proof, the very first statement you always give is just the given information, right? If I'm looking at a court case, I need to know what happened, right? So this is what happened, is I have CE and FE are congruent, and ED and EG are congruent. That's the given information. So what questions do you have about why I'm saying that that's given? Okay. Number two, it says that instead of them being congruent, their measurements are equal. What happened there between 1 and 2? Yeah, what's going on? Yeah, so I go from congruent to equal. Which of these reasons tells me I'm allowed to do that? Go from congruent to equal. Yeah. The definition of congruence, right? I'm going to put def of congruent, right? The definition of congruent. If I go in between congruent and equal, it's because it's the definition. Number 3, C to E plus E to D gives me C to D. What just happened there? The segment addition postulate or property, right? So seg addition postulate, right? Because I took each of the little parts and added it to get the whole thing. Look at number 4. What's the difference between number 3 and number 4? What's changed? Which ones? So these ones seemed to have swapped around, right? Well, think about it. We know Number 3 says CE plus ED is CD. Okay? But CD, right, all the way across, we substituted those in. You see how we substituted those in? Yeah, we just substituted. So substitution. Yeah. Number 5, what's going on there? FE plus EG is FG. What's going on? Segment addition postulate, yeah. It's the same reason as what we had for number 3. Before I move to number 6, what questions do you guys have about how I'm lining this logic up? Okay, I want you to look at number 6. In number 6, you see how both of these are equal to FE plus EG? Look at numbers 4 and 5. Both of them say FE plus EG, but they're equal to different things. But wait, if I'm equal to something, and then that's equal to something else, aren't they all equal? So what reason could I give for saying CD equals FG if they're all equal to each other? They're not swapping. It's not equal to itself. You're really close. The transitive property. Because if I have FE plus EG equals CD, but it's also equal to FG, you see how it gets to the destination? They're all like equal to each other. So if they're all equal to each other like this, we call this transitive. The transportation goes all directions. And then the last one, what's the difference between number 6 and number 7? One is equal, one's congruent. So what reason can I swap it? You can use the same one more than once. Definition of congruence. This is what we've been building to. Last week we spent a lot of time understanding logic, making sure that things sequence the right way, because sequencing is what is super valuable here. Now that we understand sequencing, when we spend time understanding the reasons, all we have to do is sequence the reasons to make sure all the dominoes line up. So if we start with the given, we get the court case verdict we're looking for. Okay? We fixed our car the right way. So what questions do you guys have about example 1? We're going to hold off on example 2 till tomorrow. The rest of the time, what I'm going to have you do is practice this together on another example at the boards, okay? Just to see, as you guys can practice this together, what's going on here. So you're welcome to take these notes with you as you go back to your board.